My name is Konstantin. I'm a PhD student at Alltogether Aachen University, but this is joint work with my colleagues and also colleagues from Technical University of Munich. And we looked into using ECN with QUIC. We already heard that QUIC can use ECN. And we looked at it in the wild and made a large-scale measurement campaign to check whether it can be used. But before getting into the details, let me give you a short recap on ECN and how it can be used. So let's say we have a transport connection and we are not using ECN at the moment, and everything is fine. Packets are sent from our sender and are received at our receiver, and our receiver just acknowledges this. But we can see that one of the routers already has a filled up queue. And when we get to the point, of course, when the queue is full, packets are lost. And then, of course, our ACK stream is interrupted. And our sender has to wait some time until it triggers a retransmission. And then it can also reduce its sending rate, for example, to then relieve the congestion. What we do with ECN is that we mark packets instead of dropping them during the congestion. So when our router sees that the queue is filling up, it can mark the packet now, but can still forward it. And this marked packet is then received at the receiver, and the receiver can acknowledge it, but can also tell the sender, okay, there has been some congestion on our path, please reduce your sending rate, and then the congestion is relieved. This, of course, requires some interaction on the network layer, so our routers have to mark packets, and on our transport layer, because our end hosts have to send back this information to the sender. And on the network layer, we have a 2-bit ECT field. This basically tells routers that ECN can be used. So this is signaled by using ECT0 or ECT1 signals. These signals have the same meaning at the beginning, but now have a different meaning. I will get to that in a minute. And then there's also the congestion experience flag, which is basically used by the routers to mark the packets. And of course, our transport layer has to mirror this congestion experience back to the sender, so that it knows that it has to adjust the sending rate. However, ECN has been standardized after TCP and IP have already been standardized. So TCP has to negotiate ECN support. There's a lot of related work on this, which sees that from its introduction in 2001 up to now, we see a rising support. But this related work also found path impairments, which can hinder ECN. Of course, if there's a router on the path, which basically just removes the ECT fields, or if there's a middle box which changes the meaning of these fields, this can, of course, impair ECN. With QUIC, stacks should support ECN right away. In the RFC of QUIC, it's said that it's a must that every QUIC stack has to basically mirror this ECN signals back to the sender. However, this is kind of opaque. It also says in the next sentence that a QUIC stack can decide to not do this, although it's a must. So there's also an erratum on this, where this sentence should be changed. But what QUIC does is that it has some code pointers, so it's not mirroring just CE, but also the ECT0 and the ECT1 information back to the sender, and the sender can then do some ECN validation. And some stacks also already support L4S, which is reusing these ECT0 and ECT1 fields to distinguish between different traffics. So this is the point where the signals ECT0 and ECT1 now have a different meaning than before. But related work also finds there's very low ECN usage on UDP port 443, which is basically used for QUIC and H3.3. So we see that there are new stacks, completely new protocol. There's this new ECN validation method, and we see hints for low usage. So the question is whether ECN can be actually used with QUIC. And for this, we look at whether stacks are mirroring ECN, where they are not doing so, and whether ECN validation always passes. Okay, so let's get into our results. And what we do is that we visit websites via H3 and log ECN counters. And we do this for the Alexa, Trenco, Umbrella, Majestic top lists. These are top lists based on DNS or somehow other computed top lists. So for example, the Alexa top list reused toolbar information. And then we also have the ComNet.org domain lists, which we then scan basically for QUIC and ECN usage. And what we can find is that of 2.7 million domains of our domain top lists, we see that around 1/10 supports QUIC, and only 3.3% of these QUIC domains basically also support ECN. For ComNet.org, we see that 180 million domains were scanned by our measurements, and only 17.3 million support QUIC, and of these 5.6% support ECN, so are mirroring back ECN signals. So given that mirroring should be actually mandatory, we see a very low support. We then also looked into the hosts which are involved, which is a lot less, but we also see a higher support among hosts and among the domains on a relative scale. So we see that fewer hosts are accountable for more domains which are not supporting ECN. So this is a potential hint at content centralization and content provider stacks not supporting ECN. We analyzed this further and looked into the ASs which are involved. And indeed, we find that the big hyperscalers such as Cloudflare, Google, Fastly are not supporting ECN. But we see that smaller ASs, and for example, also which are then using Lightspeed HV3, and for example, Amazon CloudFront CDN is using ECN. And we also see some tests by Google where suddenly ECN has been mirrored. Okay, so we see that only a few domains supported. The question is now why? And this could be either due to stacks that are ignoring ECN or due to the network clearing code points. So it could be that a stack is not receiving any ECN code points because one of the routers on the path is simply removing the information. And for this, we are using Tracebox. We already heard about traceroute. Tracebox is a traceroute variant, you could say. And similar to related work, we are using this to trace the paths of all the domains that are supporting ECN and which were not supporting ECN. And we found for 97.5% of the domains that there hasn't been any visible ECN clearing for this path. For 2%, we found a visible clearing, and for 0.5%, we didn't trace this as we are subsampling our measurements to relieve the network. And for this 2% where we saw the visible clearing, we saw a single tier 1 ISP, which impacted 98.6% of these domains. This especially affected smaller hosters, especially after we saw route changes in December 2022. We are doing our measurements from Aachen here, which is using the German research network. And there has been some route changes at the beginning of December from one ISP to another. And after that, we suddenly saw a rapid decrease in ECN usage here. But what we can also see is the missing support by content providers. These were not routed through this ISP, is not due to clearing. So we even tested whether they support ECN via TCP. Most of them do. So either the QUIC stacks or undiscovered middle boxes on the path are simply removing ECN here. Okay, so now we see that a lot of QUIC stacks are not supporting it. There are also routers. But the next question is, just because ECN is mirrored, it doesn't mean that it's also used by our transport connections, because QUIC requires an ECN validation to use ECN. And basically, this ECN validation checks whether the first packets have had a timeout, so whether there has been some ECN blackholing, for example, so routers that see ECN signals simply drop packets, or whether there have been wrong code points set, so we are using ECT0, we are signaling ECT0 at the beginning, but our reply basically says ECT1, so there has been some change on the path, or whether we saw missing or undercounted code points. So for example, when the path changes, that one router does not support ECN anymore, but at the beginning, the path supported ECN. And we looked into this and found that 0.2% of the ComNet org domains only passed this validation. So a lot of domains failed this. And 96% of the mirroring domains that failed basically failed due to two reasons: undercounting and remarking. For undercounting, we've mainly found the Google AS. Here we see very weird scenarios where suddenly we see only one packet, for example, marked with ECN. Already we are exchanging a lot more packets, or we're seeing a lot of marked packets, although we are only not marking our packets at the beginning. And related work suspects that Google is using some kind of data center TCP inside its data centers. And it could be that QUIC, for example, here leaks internal data center TCP states through its connection. And another way that we found that ECN is undercounted is the Lightspeed server, which we already heard at the beginning that the smaller hosters are using. And here at the connection initialization phase, ECN was still mirrored, but at some point the implementation switches between packet spaces, and from that point on, ECN is disabled. For the remarking, we again found network elements of the tier 1 ISP. So there are not just clearing code points, but also rewriting code points in the routers. And again, Google's AS, probably again due to the data center TCP usage. Okay, so what does all of this mean altogether? ECN with QUIC is challenged due to multiple effects. We have seen that several QUIC stacks do not mirror ECN. We have seen that some network elements clear signals, and we have seen that often ECN validation fails due to stack and network impairments. However, what we also saw in our paper is that usage is not limited just here in Aachen, but also on a global scale. On the global scale, we do not see more than 0.4% of past ECN validation. So basically with all of the domains, or let's not say all of the domains, but with many of the domains that are supporting ECN, QUIC, ECN cannot be used. And we also saw that the usage is limited for IPv6, because especially the hyperscalers are using IPv6 and the smaller hosters often do not support it. So the ECN validation ranges are even lower in that regard. We also saw this on a longitudinal scale, but I will get to that in a moment. However, this is not just interesting for ECN, but these findings also present challenges for novel ECN mechanisms such as L4S. As I already said, a lot of QUIC stacks are already supporting L4S, but L4S can also be used with TCP. And it's very important that the ECT0 and ECT1 signals are not changed. We saw a lot of these ECT0 to ECT1 remarkings on our path, however. And this remarking is detrimental because then traditional and L4S traffic mix up in the same queues. Traditional traffic gets a lot of ECN signals. For example, a lot of congestion experience signals, and the L4S traffic and the traditional traffic mix up in the queues, so we also have higher packet loss here. But this is the good thing that we saw in our measurements. The trend is probably to be increasing. We see a lot of changes over time and a growing trend. There's an RFC erratum, which may trigger rework of QUIC stacks. It will probably not trigger 100% support, but we already see a lot of changes in stacks. And we also have open tickets with stack vendors, and an ISP already debugs its routers to see why ECN fields are changed here. This is it. Thank you.
Excellent. Thank you.